During this lesson, you will describe the magnetic field around a current-carrying wire. You will apply right-hand rules to determine the direction of fields around both straight wires and solenoids. You will explain how an electromagnet works, listing factors affecting its strength. You will explain how electromagnetic induction works to induce a current in a magnetic field. Finally, you will compare and contrast the operation of generators and motors.
Imagine your everyday life without talking on the telephone, or watching TV, or listening to a radio or playing a CD. Imagine not being able to use anything that plugs into an electrical socket. What kind of life would the teenager we just saw have without those electrical devices? What would any of our lives be like if scientists had not discovered the link between magnetism and electricity, and how to use one to make the other? Yes, electricity can produce magnetism, and magnetism can produce electricity. Some very smart people figured that out, and I'm really glad they did. It all started with a high school teacher. You heard right. In 1820, a very smart Danish teacher named Hans Christian Ørsted was doing a demonstration involving an electric current. And just like some teachers you might know, he hadn't cleaned up from his last demonstration. So a compass was near the wire. Ørsted observed that when a current ran through the wire, the compass needle was deflected. Instead of ignoring what he saw or explaining it as something wrong with the equipment, Ørsted became the first to announce that magnetism was related to electricity. Today, we know these important facts. Better get them in your notes.
You already know that an electric charge at rest is surrounded by an electric field. Ørsted discovered that an electric charge in motion is surrounded by a magnetic field.
You can see for yourself that a static charge, like the one on this balloon, does not produce a magnetic field. The compass needle is unaffected when it is brought near the charged balloon. But watch as an electric current flows through this wire, and iron filings are sprinkled around it. The filings respond to the magnetic field, which encircles the current-carrying wire. We'll have to go into the lab to determine the direction of the magnetic field around the wire. But first, you need to get a copy of the diagrams you'll use to record your observations. Local teachers, turn off the tape and give students the lab report sheet for program 10-3 in the Facilitator's Guide.
Here are the diagrams you'll use for Part A in the lab. To make directions easier to describe, north, south, east, and west geographic directions are labeled on the apparatus. In case number 1, the positive and negative poles of the battery terminals will be connected here and here so that the current will flow from geographic south to north, like this. Remember that conventional current is from positive toward negative. These two circles represent compasses. This one is placed above the wire, and you can see that this one is underneath the wire. You'll draw an arrow to show the direction of the magnetic field, which is the direction the north pole of your compass needle will point.
In Part A, a simple circuit is built with a battery, a switch, and this metal rod. We'll use the horizontal part of the rod first to test the direction of the magnetic field around a horizontal conductor. Notice that all the geographic directions are labeled on the apparatus. In case number 1, the negative pole of the battery is connected to the north end of the rod so that the current will flow toward geographic north, as your diagram shows. We'll place the compass needle above the horizontal conductor and close the switch. The north pole of the compass points east instead of the direction it usually points. So there is a magnetic field above the wire. In diagram 1, draw an arrow on the compass above the wire to show the direction of the field. Remember, the direction of the field is the direction the north pole of the compass points. When we place the compass underneath the conductor, the needle points west. Draw an arrow on the compass beneath the wire to show the direction of the field. You can see that the magnetic field is circling around the current-carrying conductor. Now we'll reverse the direction of the current by switching the poles of the battery connected to the ends of the rod. Now the current flows from north to south, as seen in diagram 2. When the compass is placed above the conductor, it points west. And when it is placed beneath the conductor, the needle points east. Draw arrows on your lab sheet to indicate these directions. You can see that the magnetic field has reversed.
I'm going to give you the rules we use to predict the directions of magnetic fields around current-carrying wires. But first, I need each of you to raise your right hand. Local teachers, make sure that all your students have their right hands in the air. Good. No, I'm not going to ask you to swear. I'm just making sure that you know your right hand from your left, because you're going to need it to follow these rules. They're called right-hand rules, and we're going to give them to you rather than have you memorize them, but you will have to learn to use them. Right-hand rule number 1 describes the magnetic field around a straight conductor. Get this in your notes.
The first right-hand rule describes the direction of the magnetic field around a straight conductor. When a straight wire is grasped with your right hand, with your outstretched thumb pointing in the direction of the current, your fingers will curl in the direction of the magnetic field.
Try it with me, using your pencil to represent the wire. In fact, let's use the rule to check our lab results. In case number 1, my thumb points in the direction of the red arrow, which shows the current direction. I'm holding the wire loosely so that my fingers are flat on top of my pencil to represent the compass on top of the wire. My fingers are pointing to the east side of the paper, the same as you observed in the lab. Now, I'll turn my hand over so that my fingers are under the pencil, and my fingertips point toward the west side of the paper. If you're doing this along with me, you can see it clearly. You have to be a contortionist to get your hand in the right position on some of these. Sometimes it's better to turn your paper around. And remember that if the field points in one direction on top of the wire, it will be the opposite beneath the wire, and vice versa. That fact could save you some hand cramps. Now, use your right hands to verify your lab results for case number 2. So far, we've limited ourselves to 2 dimensions on a page: top-bottom and left-right. But sometimes we need to describe a third axis, going into and out of the page. For that, we'll need to draw a circle to represent a cross-section of the wire. Now imagine that this arrow is coming toward you, out of the paper. You see the tip of the arrowhead. So a circle with a dot means out of the page. But turn the arrow around so that it is moving into the paper, and you'll see the feathers make an X. A circle with an X means into the page.
In Part B of the lab, 4 magnets will be placed on a platform around a vertical wire. In this view, you're looking down on the platform, so this is a cross-section of the wire. And the dot tells you that the current is moving up out of the page in case 1. In case 2, the X tells you that the current is moving down into the page. Before we go to the lab, see if you can use the right-hand rule to predict how each of the magnet needles will move in each case.
To map the magnetic field around a vertical conductor, we'll place 4 small compasses on the platform around the vertical rod. We'll connect the negative pole of the battery to the top of the vertical rod so that the current will flow up the conductor. When we close the switch, the north poles of the compasses painted blue will show the direction of the magnetic field around the conductor. Draw arrows on your lab sheet to indicate the direction. Now we'll reverse the battery connections so that the current will flow downward through the conductor. When the switch is closed, the compass needle reverses directions. Draw this pattern on your lab sheet.
Did you predict correctly? All you have to do is place your right hand on your paper with your thumb up or down. Then, just look at your fingers. They'll be curling counterclockwise when the current moves out of the page, or clockwise when the current moves into the page. And the compass needles will follow the magnetic field. If the magnetic field is counterclockwise, the 4 compasses will turn like this. And if the magnetic field is clockwise, the 4 compasses will turn like this. It's as easy as that. Now, let's do something different with our wire, like coiling it around a pipe. If I removed the pipe, we'd be left with a linear coil of wire. And wouldn't you know, this has a name and its own right-hand rule. Don't worry, you won't be asked to answer questions involving this rule. However, get it down in your notes because it will help us explain other things.
A solenoid is a linear coil of conducting wire. Right-hand rule number 2 is when a solenoid is grasped with the right hand so that the fingers curl in the direction of the current, the outstretched thumb will point toward the north pole of the magnetic field.
Now, how does a coil of current-carrying wire wind up acting like a bar magnet? Let me show you. This tube represents the wire. When it's straight, a magnetic field circles around the wire. These arrows represent the direction of the field. Now, let's coil it around this tube. Look what happens to the arrows. They line up and all point in the same direction. So, this must be the north pole of this solenoid. You can see the field better with this solenoid embedded in a sheet of plexiglass. Iron filings are sprinkled around the coil. When the current is turned on, the filings line up with the magnetic field. You can see all the filings turning in the same direction within the coil. You may have heard of a solenoid before because it is an essential part of a common device. All we have to do is add a soft iron core to intensify the magnetic field inside the coil, turn on the current, and we've made an electromagnet.
An electromagnet is a solenoid with a soft iron core. Electromagnets are much stronger than other magnets and have another big advantage. Watch.
Another difference between an electromagnet and a regular magnet is that an electromagnet can be turned on and off rapidly. When the flow of electricity is shut off, the magnetic action stops.
Let's go to the lab to watch our students turn a nail into an electromagnet and test 2 factors that affect the strength of the magnet. As you watch, take notes on how to make an electromagnet stronger.
This nail is made of iron, but it is not a magnet because its domains are random. To turn it into an electromagnet, we'll coil half the length of a coated wire around the nail and attach the ends to a 1.5-volt battery. When current flows through the wire, the nail's domains line up and it becomes a magnet. When the switch is opened, the nail loses most of its magnetism and drops almost all of the staples. We'll count them. It's 6. To make the magnet stronger and able to pick up more staples, we'll increase the number of coils around the nail. You can see the electromagnet is now stronger. It picked up 19 staples. Next, we'll add another battery in series to make a 3-volt battery, which will furnish twice the current. This time, the electromagnet picked up 23 staples.
Okay, we've seen how electricity can produce magnetism. So now, let's turn it around. If moving electric charges can produce magnetism, could a magnetic field be used to make charges move? That's exactly what Michael Faraday wanted to do. In 1822, he wrote a goal in his notebook: convert magnetism into electricity. Almost 10 years later, he and Joseph Henry, another smart high school teacher, independently made the big discovery that changed the world. Their discovery was electromagnetic induction. Get this in your notes.
Electromagnetic induction is the process of generating an electric current in a circuit by simply changing a magnetic field. To induce a current, magnetic field lines must be cut perpendicularly by the relative motion of the magnet and the conductor.
Can it be that simple? Yes. All I have to do to induce a current in this wire is to move it up or down inside this horseshoe magnet, so the magnetic field lines are cut perpendicularly. If I move the wire sideways, no current will be induced. Now, there's another way to change the magnetic field and induce a current. All I need is relative motion between the conductor and the magnetic field. So I can take a magnet and move it in and out of the wire loop. Now, the current I'm inducing is very small, but it can be measured. Watch this.
In this demonstration, a coil of wire is connected to a galvanometer, a sensitive instrument designed to measure very small currents and their directions. When the north pole of a magnet is moved into the coil, the galvanometer needle shows that a current is induced in one direction. Notice that when the magnet stops, no current is induced. And when the magnet is moved in the opposite direction, the induced current reverses direction too. When the number of loops in the coil is increased, the magnitude of the induced current increases as well. That is because more wire loops cut through more magnetic field lines. Can you think of 2 more factors that will affect the magnitude of the induced current? Tell your teacher. The 3 factors affecting the magnitude of an induced current are the number of loops in the coil, the strength of the magnetic field, the speed of the relative motion between the magnet and wire.
Did you come up with the 3 factors? They make sense when you think about cutting more magnetic field lines to create more current. Let's go back to the first example of moving a wire inside a horseshoe magnet. See if you can figure out the direction of the induced current. I feel right-hand rule number 3 coming on. Here it is. When I hold my right hand and fingers like this, my thumb and fingers are perpendicular to each other, and each represents a different thing. The first thing to do is use your fingers to point in the direction of the magnetic field, toward the south pole of the magnet. Next comes your thumb, representing the direction that you move the wire. And finally, we need a third direction, perpendicular to the other 2. So, imagine pushing with the palm of your hand. That's what happens to the charges in the wire. They're pushed in this direction to produce a current. So your pushing palm represents the direction of the induced current.
If I use this magnet with the south pole on the left and pull the wire up through the magnetic field, my hand shows that the current will come out of the page toward you. You don't have to answer questions using this rule, but you should note that the magnetic field, the motion, and the current are all at right angles to each other. Michael Faraday used this idea of electromagnetic induction to invent the electric generator. This simple one consists of a loop of wire called an armature that is free to rotate inside a strong magnetic field. As the armature turns, it cuts the magnetic field lines and induces a current. So a generator converts mechanical energy into electricity. Get this in your notes.
The electric generator was invented by Michael Faraday. It converts mechanical energy into electric energy. A generator consists of a wire loop called an armature that rotates in a magnetic field to induce a current.
The discovery of electromagnetic induction and the invention of the electric generator truly changed the world. It ushered in an age where making electricity in large quantities is so commonplace that it lights up our cities and runs our industries. All we have to do is find a way to turn large armatures containing lots of wire loops in very strong magnets, and we've generated electric current. But don't make the mistake of thinking that producing electricity is easy, or that we're getting something for nothing as far as energy goes. By now, you've learned that this just doesn't happen. Do you remember this device from an earlier program? It's a handheld generator, and it works just like the ones I've described. But the more current I generate, the harder it is to crank the handle, and the more work I have to do. Why? Put your pencils down, get your right hands ready, and watch.
We've already used right-hand rule number 3 to figure out that when a wire is pulled upward through this magnetic field, the induced current is out of the page toward you. Well, what happens when a current flows in a wire? Tell your teacher. When a current flows through a wire, a magnetic field encircles the wire. Use your right hand with your thumb pointing in the direction of the current, which is out of the screen toward you, and tell your teacher whether the magnetic field viewed from your perspective is clockwise or counterclockwise. It's counterclockwise, like this. Now, look at the magnetic field above the wire. It's in the same direction as the magnetic field inside the horseshoe magnet. So when we pull the wire upward to induce the current, the magnetic fields repel and we would feel resistance and have to do work to overcome it. Watch this. As before, the wire coil is attached to a galvanometer to measure the induced current. But this time, the coil is suspended by strings so that it's free to move. Let's see what happens when the north pole of a bar magnet is moved into the coil. Why does the coil swing away from the magnet when a current is induced? Because a magnetic field is created in the coil by the induced current, and the direction of the field opposes the motion of the magnet into the coil. This is stated as Lenz's law.
Lenz's law states that an induced current always opposes the motion that induces it. This means that work must be done to overcome the repulsion of the magnetic fields.
So, the more current that is induced, the stronger the magnetic field that forms around the wire, and the more repulsion has to be overcome. Nope, you don't get something for nothing. Electricity is not a source of energy. It's a form of energy that has to come from another source. Generators convert mechanical energy into electric current. Now that brings up another electromagnetic device that is very important to modern life. It's the motor. If you understand that moving a conductor in a magnetic field produces current, then all you have to do is turn that around, and you have the principle behind a motor. An electric motor has the same basic parts as a generator. But a motor converts energy in the opposite direction, from electric energy to mechanical energy. In a motor, current runs through the armature coil inside a magnetic field, and a force is exerted that makes the armature turn.
A motor consists of a coil of conducting wire placed inside a magnetic field. When the switch is closed to allow current to flow through the loop, a magnetic field surrounds the coil and repels or attracts the stationary field magnet. As a result, the coil turns around. A motor is a device that converts electric energy into mechanical energy, like the energy used to turn the blades of a fan.
So, motors and generators have the same parts, but work in opposite directions. In fact, the mouthpiece of a telephone is a generator, converting the vibrations from your voice into electric impulses. And the earpiece is a motor, converting the electric impulses back into motion to vibrate the speaker and produce sound. Both mouthpiece and earpiece contain magnets and are electromagnetic devices. You should read more about AC and DC generators, power transmission, and the working of transformers. And your teacher may want you to pick an electromagnetic device, like a cassette tape player, an electric guitar, a doorbell, or a TV, and describe to your class how they work. You haven't heard the last about this connection between electricity and magnetism. We've just scratched the surface. For our next unit, get out your shades and sunblock, because we're heading to the beach. Well, not exactly. We will be studying waves, including electromagnetic waves. We'll learn a whole new meaning to the phrase, "Surf's up, cowabunga, and good luck on your unit test. Catch you later, dudes and dudettes."